Great, so our first speaker now is Dr. Sadie Jones with Mysterious Supermassive black holes. Can we please welcome her up with a round of applause?
Okay, hi everybody. Hi, my name is Sadie. So I am going to talk to you actually not about hungry supermassive black holes, but a mysterious supermassive black hole, which was the subject of my PhD, which I finished back in 2012, so a long time ago, but it's still having quite an effect on me, and I like to talk about it to kind of get myself through the trauma, if you like. Okay, so to show you that scientists are kind of normal human beings, other than kind of doing their science research, I've just got a bit of a slide to show you that I do have hobbies outside of astrophysics. So I'm Welsh. My mother is deaf, which is why I don't need a microphone. I did my master's in Cardiff in astrophysics, came here to do my PhD, and now my job is taking a mobile planetarium into schools mainly, but also talking about all the research that we do in the physics and astronomy department in the University of Southampton. I love to travel, which is really handy because astronomy has lots of nice telescopes in very nice locations. I got to go to Chile with Charlotte, who you just saw, over Christmas to observe. I just came back from Japan, which is why the talk title is incorrect, because I wasn't very good with the emails back and forth. I'm also trained to become a science comedian, because that is a thing, apparently. I did a gig actually at Eastleigh Open Mic Night, which was fun, because all the other gigs have been to a strictly science audience, and these guys were not necessarily, so that was interesting. And I also play a sport called roller derby, which is like rugby on roller skates, so that's really fun. But enough about me, I guess. Onto what you're all here for, black holes. These dark beasts. Okay, but black holes are black. So does anyone know how we actually see them, or observe them, or measure them? Come on, someone knows. Anyone?
You look around them?
Sorry?
You look around them?
Yeah, you look around them. So we're looking, this is obviously an artist's impression. I haven't taken a video this close to a black hole successfully. But even though the black hole itself kind of has such a large gravity that all light goes in, does not escape, we can see the effect the gravity from the black hole is having on the interstellar medium, if you like. So as stuff swirls into the black hole, it kind of changes from having lots of what we call gravitational potential energy to kinetic energy, and we see it kind of radiating light as it swirls around. For the stuff I study, supermassive black holes, we can actually see them in all types of light that exist. So this is something called the electromagnetic spectrum, which a lot of you might remember from GCSE, hopefully. So we have radio waves, which are really, really long wavelength, all the way to gamma rays, which are really short wavelength. So the shorter the wavelength of the light, the higher the energy, okay? So things like black holes, you can see X-rays coming from the stuff very close to the black hole, where stuff is very hot, everything has a lot of energy and is moving around, so you get things like X-rays and gamma rays from that. You also get radio waves, because whenever you accelerate an electron in some kind of magnetic field, you will see radio waves, basically. So as an astronomer, what we normally do is observe a star, a galaxy, a black hole in at least two of these different parts of the spectrum and compare what's happening to try and understand it. And that was basically what my PhD was about. But kind of reeling us back in a bit, does anybody know what this is?
The sky.
It is the sky, very good. You can't really see very well, but you should be able to see like a kind of smudge up the middle.
Milky Way.
Milky Way, yeah. So this was actually taken on a really crap camera, actually, in my my friend's back garden. So in the South Wales valleys, outside of the city, basically. deepest, darkest whales, you can just about see the Milky Way. If you go to the Brecon Beacons, which is a dark sky site, so if you Google dark skies UK, there's lots of sites now which you are like guaranteed to be able to see the Milky Way if you go there. So I think the Isle of Wight has it now, the South Downs Way has it. So if you want to see the Milky Way, you don't have to go that far from Southampton, you can see it. But normally when we do astronomy, most of us think of optical light or visible light, which is because, and we think of that because we can see in that part of the spectrum with our eyes. Our eyes are optical light detectors. So that is why black holes, for example, are so mysterious and dark. Okay, when we want to take a picture of something with optical light, we need to think about resolution. So even though you might not have heard of angular resolution before, you definitely would have heard of the concept, because if you have a mobile phone, for example, if your friend has like 12 megapixels on their phone and you only have 5, then your photos will look really blurry compared to them. And their photos of you, if they've got 12 megapixels, they'll be so detailed you'll be able to see all their spots and all their imperfections. So for taking, selfies that look really nice, having lots of megapixels is maybe a bad thing. But for looking at the sky, for astronomy, we want lots of pixels across our image so we can have really high angular resolution. So for the wavelength of light, anyone know the wavelength of light? Might remember it from the slide. It's about 500 nanometers, so a really, really small number here. And if we're dividing it by d, which is just the size of our telescope in this case, so sorry, the size of the lens, the number here, angular resolution, is going to come out quite small because you've got the 500 nanometers on top, and that is a small number. So it doesn't matter if your lens or your mirror is like this big, like 20 centimeters or so, you're still going to have a really small angular resolution, a really small pixel size, and you're going to be able to see really good detail of whatever you're looking at, if it's a black hole or a star or a galaxy. And a nice little spin out from astronomy is actually the cameras you will have in your smartphones actually is technology that was invented to look at stars in really, well, anything in the universe in really great detail. So it's called CCD technology. Okay? So astronomy is good. Make sure you all realise this. But the problem we have on the Earth, obviously, is that we are...
Bingo!
Whoa, well done. Wow, we're going to remember that word. Okay, keep going. Well done. It's okay, I just bit scared. So the problem we have on the Earth is that the atmosphere stops being able to see the stars. This isn't necessarily a problem, because if we didn't have the atmosphere, well, A, we probably wouldn't have evolved anyway, but we would have all these X-rays and gamma rays coming at us from space that would be incredibly harmful. So the atmosphere is good, but as an astronomer it's a little bit bad, because it makes the stars twinkle like this, okay? So that's where we stick our telescopes out in space, and Hubble is probably one of the best known telescopes because it has such a good angular resolution, okay? So its angular resolution is about 20 times better than the twinkling, okay? So the angle of the twinkling in stars, you can't see stars to any better angular resolution than the twinkling. Okay. Not sure I'm explaining this very good, but this will show you what I mean, hopefully. There you go. So with a telescope like Hubble, or even some of the really, really good ground ones that can, they use lasers to get rid of the effect of the twinkling, you can get images like this. So this is much better than my friend's image of the Brecon Beacons. But still, this isn't the whole story, because you have all this black area, the dust and the gas is in the way of the stars. So you can obviously learn stuff about the brightness of the stars. You can learn some things, but you don't have the whole picture because you're only looking at one part of the electromagnetic spectrum. So this is now the Milky Way.
Sorry to interrupt.
It's okay. This is the Milky Way in all the parts of the spectrum, so you can see it looks quite different. So this is your optical one that you just saw. Gamma ray here, and then radio at the top. So why do you think the radio is very bright? It's a very bright area at the centre. Anyone know why Yeah, so the galaxy has a supermassive black hole in the middle that shows very brightly in radio. But down in this one, in gamma ray, the black hole is quite bright as well. But anyone know what this could be? Something very bright but off to the edge of the galaxy in the arm. It's not a quasar, good guess. It's a supernova. So there was a big exploded star that went off, and there's still gamma ray radiation coming out of that area. So if we just looked in optical, we wouldn't necessarily know that this star was still giving out such a lot of energy in gamma ray. So our supermassive black hole in our Milky Way galaxy is called Sagittarius A star, and that's just because if you look in the location of the Sagittarius constellation, that's where the centre of the galaxy is. We just call it that for it makes the most sense. We know that there is a supermassive black hole there because we have the resolution, because this black hole is the nearest one to us, or supermassive one nearest to us, to see individual stars. So we are able to track these kind of 6 stars. Can you just click on that? Yeah. So we can see the individual stars, and we know from their speeds, their distance from this central nothing, that the mass of the thing in the middle comes out to be 4 million times that of the sun. Okay? So the only thing that can be 4 million times bigger than the sun, be invisible, and in a very small volume of space, and have such a big gravitational effect on stars is a supermassive black hole. That's the only thing that physics can describe. This is a bit of A-level physics here, if anyone's interested. But it's quite a simple equation, because you can cancel out these small m's, and the only unknown in this equation then, because you know the speed and the distance, is big M. So that's how you figure out the mass of the black hole. It's nothing too elaborate, which is good for me because I've forgotten how to do maths. Yeah, so there are 2 types of black holes. There's the supermassive ones, which I am talking about today, in the sense of galaxies. These are about 1 million times bigger than the mass of the sun, so really big. And there's also these smaller ones, which are dotted around inside the galaxy, in between stars.
Bingo!
Wow, am I going to get all the bingos? We only see these smaller black holes generally if they're eating material off a nearby star, because if you just have a black hole in the middle of space, it's black, it's dark, so you won't be able to see it. But if it's actually near enough to another star to rip material off it, then you get this thing called an accretion disk forming around it. You get X-rays, radio, basically exactly the same as the one in the centre of the black hole. And there's lots of research at the university to see if these are like, the big ones are like scaled up version of the small ones, and the small ones are a lot easier to see. There's a lot more of them in the galaxy. We've only got one supermassive black hole we can look at. If you want to know how these smaller black holes are made, then in the breaks, Charlotte here and the other women in the Women Physics Network, can't even say it and I'm in it, have some supernova demos. So you make small black holes when a large star, like Betelgeuse in the Orion constellation, comes to the end of its life, it does a big supernova explosion, and the core that's left over either becomes a black hole or a neutron star, and then all the stuff gets chucked out into space and essentially gets recycled back into new stars. But this happens over millions of years. But I'm not bothered with that. I'm all about the supermassive black holes. Specifically the ones that are active, and I'll get onto that later. But hopefully most of you have seen the film Interstellar. Please put your hands up if you have. Oh, never been that many people actually. Lots of school kids haven't seen it. But maybe because it's very long, they can't sit through it. My mother got about 10 minutes in. She didn't even get to the weird bit. Okay, so we have Gargantua. Oh no, just don't look, don't look. Press the wrong button. Okay, Gargantua is really interesting because it was the first film where they actually worked with scientists. So they actually made an academic paper out of this because the graphic designers worked with scientists and modelled the best representation of a black hole that ever been in a film, basically, based on real data and real physics, real gravity, all that kind of thing. So this is a pretty good representation of what a black hole would look like if you were kind of flying towards one. But it isn't the first draft that the kind of scientists and graphic designers came up with. When they went to the director, Christopher Nolan, he made them change it a little bit because he thought you guys as a public maybe wouldn't understand it and wouldn't like this gargantuan black hole as much. So first of all, he added in some kind of flaring to make it all brighter, and also made it look very even and changed all the colour so it was very uniform. Does anyone know why one side of the black hole is more red? Yes. Very good. Yeah, so the black hole, I should have said this earlier, but black holes, they conserve the angular momentum. So planets spin, stars spin, so even when they become a black hole, they're still spinning, and they'll spin very fast because they've kind of got very compact very quickly, like an ice skater, I guess. So, so this side of the black hole will be more red because it's spinning away from you, this side will be more blue because it's spinning towards you. In the other pictures you might have noticed there's an accretion disk, which is always along one plane. So does anyone know why you see some of the accretion disk going over the top of the black hole? The black hole is spherical, but in reality, is there actual stuff going over the top as well? Or is it something else?
Light bending?
Yeah, light bending, very good, yeah. So that's actually to do with gravitational lensing. So there is an accretion disk, but the way, because of the gravity from the black hole,
Bingo.
also looks like it's going over the top. I think, oh yeah, and also to do with the spinning, that because of the spinning, the black hole and the accretion disk and everything doesn't look very uniform, whereas obviously in the actual representation, it does. So yeah, I thought this was pretty cool that it was actually that it got made into a paper, and that kind of movies and scientists are working together. So hopefully there's a job for me in the future, maybe. Okay, so this is back to a kind of supermassive black hole. So this is just an optical picture now of a supermassive black hole. Well, a supermassive black hole in the centre of a galaxy. I can't remember the name of it. It is NGC 5128. There you go. 12 million light years away. If you want it in kilometres, it's about that far away. Pretty far. So this is optical, very nice. But if you look at it in radio, X-ray, and optical, you can see there's this massive jet coming out the middle. So you see, and this jet would go off kind of hundreds of light years into space. So it's really weird, actually. How can you keep a jet collimated for hundreds and hundreds of light years? Like, what the hell is going on? And that is a question we're still trying to answer. We have no idea how the hell these things can go out into space and stay like as a column of like a jet for so long. So from the blue bit here, this is X-ray from the jet, and then you get radio when everything kind of slows down a little bit and hits all the interstellar medium. This kind of like back, I don't know what I'm trying to say. We call these like hot spots where everything's hitting and kind of like a plume of gas coming back towards you. So that's really cool. So my PhD was to look at NGC 4051. It's interesting because basically it was doing stuff, it is mysterious like my title suggests. It's doing stuff in the X-ray that you wouldn't normally expect of a galaxy of this type. If you do have a really nice, kind of maybe about a 14-inch telescope, if you have one that's quite big, you can see the galaxy is here. So if you go and look at the, I can't remember what it's called now, Cloud, Big Dipper, Saucepan, whatever you like to call it, it is just a little bit down from there. But you wouldn't be able to see it with a kind of little telescope. It's quite, it doesn't look that bright from the Earth, sadly. This is just a little quiz. Anyone want to guess? So I mentioned that I look at supermassive black holes, but they're specifically called active. And that is because they have a very bright centre, which is kind of equivalent to the brightness of all the stars in the galaxy kind of in one spot again. Okay. So which one's the active one? This one. This one. Left?
Left.
Yes. Yeah. So the left one is brighter, and you can just see that with your eyes, hopefully. So well done, you've spotted the active galaxy. So even with the optical, you can see that it's active, but then you go with your X-ray or your radio telescope and investigate further. I kind of said all this basically already, but jets are a mystery. We have no idea how they work, and that was basically where the idea for my PhD thesis came from. It was trying to see if the material that's spiraling around the black hole then kind of travels up the jet. So if you get X-ray radiation from the stuff swirling around the black hole, and you get radio radiation from stuff kind of going up the jet, then if you had two telescopes looking in those parts of the spectrum at the same time, you could understand if there was a relationship between the disk and the jet. That was the question I was trying to ask, at least. This is just a kind of zoomed in view of this to explain, but basically what we think happens is there's a magnetic field. We don't really understand how it's anchored on, but it's at the edge of the supermassive black hole. And particles that are kind of in the accretion disk, they get, instead of falling into the black hole, they get attracted along these magnetic field lines, and they spin around the magnetic field lines, and that means that they can cause something called X-ray synchrotron radiation, but then they can also be seen quite easily in the radio part of the spectrum. So I'm just pointing my telescopes, the X-ray telescope in space, the radio telescopes on the ground at the object at the same time, and trying to look at the brightness and then see if there's a correlation between the two of these things. But then there's another problem, because galaxies are not always out in space all at different angles. So if the jet is pointing right towards you, you're going to see it looking really, really bright in the radio, and you wouldn't see much X-ray necessarily. If you're looking at it at a different angle, you might see it looking brighter in different parts, if that makes sense. To show this, because I'm Welsh, I have a ball. So as someone who's been around rugby for quite a lot of my life, I know this is the Gilbert rugby ball, and it is a kind of rugby ball shape. But if I was an alien coming to Earth and I had just seen this as it is here, I might think the ball is actually spherical. Okay? It's only because I know information about the design of Gilbert and all this kind of thing. So this is the same kind of problem that we have with active galactic nuclei. Like I said, if you're looking down the jet, you see it looking very bright, but if you're looking kind of off to this angle, then it would look very different. But forgetting that for a minute, I had data from an X-ray telescope in space called the Rossi X-ray Time Explorer. This might be what the source would look like. So it's getting brighter, dimmer, brighter and dimmer. And we can make this into something called a light curve. So here you can see it gets bright, dim, and then bright again. So we're just literally looking at time. As something gets bright, oh, easy. Same with the radio, but now remember back to angular resolution. Anybody know how long the wavelength of radio waves is? It's definitely on the slide. Yeah, about 1 meter to 300 meters, so a lot longer than optical light. So if we go back to our angular resolution equation, the wavelength now is 1, so we need this d, the diameter value, to be really big, otherwise our angular resolution is going to be really crap, basically. So this is why we have something called interferometry, radio interferometry. We connect radio dishes across large distances, and essentially we have a dish the size of the distance between those dishes, okay? Rather than just the size of the actual dish itself. The telescope I used was the VLA, so if you can move these out on like railroad tracks, they're really cool. So in the A array, which gives the best resolution, the D in the angular resolution equation is 36 kilometers. So that's quite good. So you've got 1 divided by 36 times 10 to the 3, so your angular resolution is going to be quite a small number, so you're going to be able to see quite good detail. The lowest one is 1 kilometer, so it's still quite big, but ideally we want it always to be an A, because I'm trying to look at details about a black hole, really small, so I need the best angular resolution possible. This is an image that I made for my PhD, which took about 6 months to make. Yay! So it's 3 blobs. And the first blob in the middle is the supermassive black hole. And these 2 blobs are mysterious blobs. I don't really know what they were. At the time, I didn't know what they were. But it's fine. So to measure the brightness, all I need to do is just draw a box around there and measure the brightness. And just keep doing that for all my images across the days and seeing what the graph looks like. And it looks like this. Whee! So it goes up and down and up. Can anyone remember what the X-ray curve did? Up, down and up. So I'm like, yes, I've solved science. They do the same thing. But then I realised that the very large array, I didn't have control over it. So I wasn't able to say to the people at the VLA, can you please keep it in A array the whole time? So I get the best resolution. So it changed from being actually in something called C array to D array, which is the worst. Then it went to A array, which is the best, and then it went up through the other different combinations. So can now anyone think of a reason why my light curve for my black hole might be doing this? Do you think it's really to do with the black hole in space, or is it my telescope? Yes.
Is it to do with what the black hole is sort of absorbing?
That's what I thought. You're correct.
If it absorbs a brighter star, then it's going to be
Yeah.
brighter.
So originally, when I looked at the radio waves, that is exactly what I thought. So if it gets brighter, then it's kind of absorbing more material, and you'd see a flare event. So that is like the science that I was interested in. But when I realised what the actual telescope was doing, I realised that when it looked the brightest, it was in D array. So if I show you this picture now, this is when it's in D array. So the resolution is a lot worse. So now you can't see those 3 blobs that are the black hole and something weird. You can actually see the whole galaxy. So when I draw the smallest box I can draw around the centre where the black hole is, there's a lot more information, a lot more brightness, which is adding to the value, which is from the spiral arms and not from the black hole. And there's no way I can really untangle that because the telescope was in D array at the time, and I can't go there and move it to A array myself. So what I'm trying to say is this isn't real. Well, some of it might be real, but a lot of it is probably to do with the fact that the telescope was in the lowest resolution array at this point, and therefore when I drew the box around the centre where the black hole is, it just looks brighter because the angular resolution is bad. So this is the problem with science sometimes. You get excited because you think you've found something, you've had an eureka moment, and then you realise it's actually just your detector or your telescope. But anyway, I did devise a way to kind of subtract off the values that were due to the telescope. So then I could have a light curve, which I could compare with the X-ray light curve, and see if there was a relationship. And there's something you can do where you basically run these 2 light curves through a computer program, and it tries to see where they line up. So what I would be expecting to see is like a flare in the X-ray, which is from the disk, and then a few days later maybe I'd see a flare in the radio. And then the time between those 2 flares would actually tell me the size of the supermassive black hole and its disk-jet system, which would be really cool. But again, I'm only doing this for one galaxy, so it's really hard to have good statistics. But anyway, it turns out another aside is those 2 blobs were jets from the black hole, and in this galaxy you weren't expecting to see a jet. So that was interesting, and my supervisor has quite a lot of power, I guess, in radio astronomy. So he managed to get us in time on this, which is basically a radio dish the size of the Earth, because you connect all dishes together. You have really good resolution, and this is the picture I got. Woohoo! 3 blobs. But they're in a line. Yeah. Okay, so this is the black hole, and then I reckon this is definitely a jet because when it hits the interstellar medium, it's got like a plume coming out of it. But the problem that I instantly saw, and my supervisor instantly saw, is these contours are only like twice the level of the noise. So this is considered to be a 2 sigma result. Usually in science, like in particle physics as well, you need to have the signal you detect from whatever you're looking at needs to be at least 3 times the background level, or the background noise. So none of this could be real. This could all be imaginary coincidence. It just happens to be lined up. But I like to think that it's a jet, based on science and, you know, just wanting to be right. And this is kind of my final slide, but basically what scientists generally do is they take their data and try and put it on a graph and then add it to an even bigger graph to see if they can draw a straight line through it. Please don't tell me off, there's no errors in here. I missed off the errors, I'm a very bad person. But I can assure you it does go through within the error bars. Just haven't put them on because they're very naughty. But my galaxy is a supermassive black hole that lies here. All these triangles are my points. And this is called the fundamental plane of black holes. So that's really cool. So if you have the value, for example, the X-ray brightness for your small black hole, you should be able to use this graph and measure off or predict what the radio brightness will be. So that's cool because it stops you having, well, it means you don't have to use a radio telescope. You can make a prediction about the radio. The one mystery of this graph is there isn't anything in the middle. So why can you get small black holes that are like 10 times the size of the sun? You can get ones that are 1 million times the size of the sun. Why can't you get ones that are intermediate size? This is a really big mystery, again, that people are trying to figure out the answer to. Where are the intermediate mass black holes? These are some slides I've left in because I normally give this as a kind of careers talk. There are lots of radio dishes being built across the world. They need people to help them. So you should become a radio astronomer. The slight issue they have is they have so much data from these telescopes, which are across the whole of South Africa and Australia, that they have 160 gigabytes of data per second, which is 10 times the global internet traffic in a second. They have nowhere to store it. They haven't got the hard drives. They haven't got like the engineering computer possibilities to store the data. So a lot of it gets deleted. So just like in the Large Hadron Collider, where they have to delete a lot of the data, this is even worse than that. They have to delete basically all of it. So this is the problem they're trying to figure out at the moment. So it's not just astronomers we need, it's kind of engineers, people who are really good